Okay. 8 a.m. Time to go. You've probably seen if you watch like a talk show, the host will just kind of adjust his tie. There's a production assistant down at the bottom going, and good morning, everyone. We're talking Chem 1 production. Welcome back. We'll go through some material today. I'll kind of tell you where we'll stop for exam. We'll see how far we get, but more or less the end of the content today is all fair game for the exam, which I hope I can say this right, is Tuesday, July 6th at 6 p.m. Pacific Daylight Time. Goodness. I was looking through the live stream. I don't always go back and review, but looking at the live stream yesterday, it's interesting for me to, I don't have to look at myself, but look at the chat, because the chat plays back and I can see the questions that are coming in. I'm glad to see questions come in, and ask questions in the live stream. If you're not getting the answer you like, you might more clarification, you can prompt the GSIs, could you ask Mark, especially, and the GSIs will filter that if it's something that's interesting to the whole class, if I'm not being clear. Because the GSIs are there too. They can, if they don't understand what I'm saying, they will interrupt. But one of the great things about seeing the chat is I want you to ask questions. There are no stupid questions. Ask questions for one reason, for the obvious reason. Maybe I'm not being clear. You don't understand. Maybe your neighbors don't understand either. But the question you ask, I'm trying to explain this, and I'm learning as I go too. What I want to know, your questions help me understand not just what you don't understand, but why you don't understand it. So what are you thinking? I can sometimes tell, and then I can tailor this lecture, but next year's and those down, so that some misconceptions that you have, I kind of address them as we go. So anyway, one question that I saw in that, we had this thing that I called the free energy landscape, and someone asked, what the heck is the difference between a free energy landscape and free energy? This is an analogy, and it's a useful one. So what we're saying here is, if you are standing and you look out over the landscape, the physical landscape, you see hills and valleys, highs and lows. And the reason we do this is it's a direct analogy to gravitational landscape. If it's a gravitational landscape, you expect to see the water down here and all the rocks that roll downhill. Over time, things end up down at the bottom of these hills. If they end up down in the bottom here, it's not likely that they will make it over this hill on their own. There'll have to be something else to do that. So something has to give them potential energy. And that's the same thing with free energy, except it's not rocks and water, it's compounds. So we arrange compounds at various places on the hill, and we can say, well, the down in free energy is this way, so this group of compounds is more likely to become this group of compounds over time. So, and what we mean by free energy, we mean at equilibrium, we can tell which form predominates. We can tell which form is lower on the hill. That's all equilibrium is. That's all free energy is telling us. Now, so don't be shy to ask. I love it when you ask. It makes it more fun for me. I'm sitting here talking. I don't want to talk to myself. Especially in this room, we have one of your students here. More of you are welcome, but just talking to an almost empty room isn't helpful. But I love to see the questions. I like to see you learn. And if you don't understand, like, look at it this way. If I had a puppy, if you have a puppy, and it comes to the bottom of the stairs and it doesn't under the stairs the first time and it can't get up the stairs, you don't say, oh, that's a stupid puppy. You say, oh, cute little puppy, let me help you up the stairs. Let me show you how to get up the stairs, why the stairs are there. And I also teach, as you know, from this very conceptual level. We don't grind out a lot of numbers here. And that is the same kind of reason. When you leave Chem 1, I know that this is not a chemistry majors course. You're going to go to other courses. What from Chem 1 will help you in the other courses? If you can grind out moles to grams, that's fantastic. It will not help you in MCB 105 or whatever down the line. You're not going to do that again. What will help you is you understand how things combine. You understand the particulate nature of the universe. You understand why things go from one to the other. Happens in your body the same way it happens here. If you go into any other kind of science, you should have a big picture of what's going on. I want you to come away as a big picture person. The other thing is when we teach this in the fall, and we teach it here, it's thousands of students a year. And I want the students who leave Cal and go out into the world to be ambassadors of science. I don't want you to tell someone on the street how to convert grams to moles. I want you to tell them, well, this is just a big population. And what happens is that tends to move in that direction. That helps you understand so many other things. So that's why we do that this way. I want to, show you the. I want to show you the world. It's like I'm Aladdin and you're Jasmine. I can show you the world. It is shining, shimmering, splendid. Tell me, students, now, when did you just let your brain decide? I can show you the world. Show you one, I can open your eyes. Isn't that how it goes? I can open your eyes, show you wonder by wonder, over, sideways, and under on a magic science ride. It's a whole new, fantastic point of view. You look at that free energy table and you say, oh, those are the standard state free energies. I can see the hill. The things that have that lower negative free energy are higher up the hill. And I know they can come tumbling down. That's what I want you to take away. I can. Oh, that's shining, shimmering, splendid. It is. I love science because it is shining, shimmering, splendid. You look at the world in a new way and you understand how it works. Free energy and equilibrium. We were talking about that last time, and we got to this beautiful point where we understand equilibrium is kind of a simple concept. It is the bottom of that hill. So when the free energy difference between products and reactants is 0, then neither of them are favored. And it's at equilibrium. The universe is indifferent to which direction the reaction goes. You're at the bottom of that hill. Go up a little this way, come back down. Go up a little that way, come back down. That's what equilibrium is. So we understand that it's equilibrium. It's not equal amounts usually of products and reactants. There's not an equal amount on each side. There's enough to balance the free energy so that there's the ability to go back and forth. So we understood if K's are less than 1, that is a favoring of the reactants side. There's more reactants at equilibrium. And that jives with the fact that those should be delta G greater than 0. That is, that's not the spontaneous, that's not the downhill direction. So if your K is less than 1, you're not going to go downhill. You essentially already are. The reactants are farther down on free energy hill. Same way here. If K is bigger than 1, then there's a lot of products at equilibrium. So the products are down. That one, the free energy difference is negative. And it's interesting. No, I don't think I've said this forcefully enough. This all comes from the idea that for every process, the way we got here is we said for every process that is spontaneous, delta S of the universe is greater than 0. And let's drive that home. That's a fundamental point. Every process that happens spontaneously, the entropy of the universe increases. We talked about so many state functions, the energy and the enthalpy and the free energy. They're conserved. Entropy of the universe is not. The entropy is always increasing with every step. We're gaining entropy in the universe. We don't gain any energy. That's all here, and we're never going to get any more. We just move it around with heat and work. But every time we move it around with heat and work, entropy increases, and we can't get it back. We cannot win. So those products and reactants end up in equilibrium because going back and forth between them at equilibrium, that's when switching between them, the entropy of the universe is 0. There is this special case where it can be 0, but it's rare, it's microscopic. It's the time you're at equilibrium when I can shift back and forth between products and reactants and not increase the entropy of the universe. That's why we end up at the bottom of that hole. So all these things are related to that bigger issue. Crackling noises. Let's lower the gain on the mic a little. Okay, we'll try to get gain. I'll try to get a little farther from my head. It might be touching something. We'll try to get better audio. Thanks for reporting that. So keep reporting it. I hope it's getting better. So we have a beautiful understanding of chemical reactions, why they go, the implications for the universe when they go, what's driving them in that direction. It really is. Increasing entropy tells us the time direction of the universe. That's how I know this happened before that, because there was more entropy here than there was here in the universe. So we saw we could connect them together since they are clearly related. Here's the functional form of how we connect free energy and the equilibrium constant. So that's where we ended last time. So let's start out with a ChemQuiz then. We talk a lot about this standard state where I put the little degree sign. So we can measure the free energy difference anytime for products and reactants, whatever their concentrations are. But if we measure it when everything is 1 molar and 1 atmosphere, then we give it that sign. Okay? So what are the standard state free energy difference and the equilibrium constant K for this reaction, H2O liquid, H2O gas, in equilibrium at 25 degrees C. So think about those for a minute. We'll join you in the chat rooms and take a vote. I'll join the local people first for this first one, as is our tradition. I'll start the thing. And talk about it amongst yourselves. Take a vote. Test. Turn the gain down more, and hopefully we'll get a little better. Now we don't have any blue at all, so come up till you have blue. All right, let's try to run it there. Just past that, and see if that's helpful. I wonder if something's rubbing. This reaction is, I'll clarify, this reaction is in the standard state. I think I said equilibrium at 25 degrees C. It's in the standard state at 25 degrees C. So it's not the equilibrium condition. I'm sorry if I said that wrong. So take your votes. If that changes your vote, you can change it, and we'll talk about this in another about 30 seconds here. Okay, about how many people are in the Zoom? Okay, so pretty much everybody has responded, so let's see what you're thinking. Half of us think C, that's the case. So I agree with the thinking of C. Fantastic. So what's going on here? You're not at equilibrium. You know K at 25 degrees C. We've said it a bunch of times. It's 0.03. It's less than 1. It doesn't change if you're not at equilibrium. K, that's what K is. It tells you where you're going, not where you are. Q tells you where you are. So a value of K that you know, it's less than 1. So that means it has to be B or C. So the question is the free energy difference between the products and reactants at standard state 0 or greater than 1? Well, what is the standard state? The standard state is 1 atmosphere. So this would have to been 1 atmosphere for that to be the case. So Q is 1, products over reactants. K is not. K is still K. So that means the products are higher in free energy than the reactants. This reaction will go back in that direction, delta G bigger than 0. Products minus reactants, the products are higher in free energy. There's essentially too much steam there for 25 degrees C. For this K, it goes back to equilibrium. When it gets back to 0.03 atmospheres, then the universe is happy and it'll go back and forth equally. So we've talked about free energy and temperature, and we've been able to draw this. Of course, now we can replace, maybe that happened fast, we can replace the standard state free energy with the expression for the equilibrium constant, minus RT ln K. That's the standard state free energy, and that's equal to the delta H minus T delta S. So we can plot a couple things. Here, I've rearranged it. And this is another expression between the equilibrium constant, but now between the enthalpy and the entropy of the system. So again, we get back to that handy state where we're talking about just system variables, and we can look up some of them. We can often find these, but you may have, so you can look up enthalpies, you can measure heats evolved and get enthalpies, but you may have been saying to yourself, this entropy thing, this counting of microstates, how do we really get those numbers? It's not something where you can just put it in a calorimeter and measure the heat coming out. Sometimes if you're very careful, you can get a heat and use the thermodynamic definition of entropy. But let's say you do this. You measure the equilibrium constant at a bunch of different temperatures. And you measure the enthalpy change. Those are all easy things. Change the temperature, do the reaction. Change the temperature, do the reaction. You can measure Ks because when it's at equilibrium, you can measure concentrations and pressures. That's easily measurable. Temperature, easily measurable. And the heat coming out. Or maybe you have a table and someone has done that in advance for you. If you do those things, this looks linear. Natural log of K, if you plot natural log of K versus 1 over T, you should get a straight line. The slope is the enthalpy over this constant R, but the intercept is the entropy change. So you can read the entropy change off your graph. It's where it intersects the y-axis. So this is a powerful thing. That's why I know you say, oh no, not another equation. But this is a way to understand how you could get to these entropy changes. So we looked at exothermic reactions and we saw how K's decrease with temperature. We looked at endothermic reaction and saw how K's increase with temperature. So that would be reflected. These are exothermic and endothermic. So that would be reflected in the slope of these lines because that's the enthalpy change. So if the enthalpy change is positive endothermic, then there's a minus there. That's going to have a negative slope. And vice versa. Negative delta entropy change, exothermic, it'll have a positive slope. And this is the point we're interested in if we're trying to come up with some entropies. That's the entropy change over the temperature. Or, oh, shoot, over R. Okay, so we'll just plot a bunch of them out. So here's the free energy change versus enthalpy and or free energy change versus temperature. Here's natural log K versus 1 over the temperature. And we know these, these will correlate. So if delta H is positive, delta S is negative, we can draw that here, positive slope and positive intercept because it's minus delta T, or minus T delta S. And here, the slope has to be negative because that's positive. The intercept has to be negative because that's the same sign. So you can just plot these out, sketch them out for various cases. And the reason I do this, so there's not a lot of chemistry classes where you have all had chemistry. Did you guys do a lot of just sketch the, they're all shaking their heads, what? So this is new for them too, but you can see why I do it. This tells you there's a lot of important points on these curves. And if you can sketch the curve, you're telling me you understand the whole thing. You don't just understand how to plug numbers into here. I know that most of you can plug numbers into here. That's how you got here. Now I want you to leave with more power. Understand what's going on. And as you know, these 0 points in free energy are interesting points that you'd like to know about. That's telling you where there's an equilibrium in the system. In this case, it would tell you where the standard state was in equilibrium. Okay. There's the last one there. And you can see how these vary with the signs of the enthalpy and the entropy changes. All system variables and many system variables you could look up in tables and do delta H of the products minus the reactants or entropies of the products minus the reactants and draw these out. Or if you were in the lab, you could measure these parameters. Okay, so here's a plot of ln K versus 1 over T. And it's for, we're always doing these vaporizations and sublimations because they're so simple to think about the entropy and the enthalpy changes. So that part is out of your head. And this again is what makes it conceptual. If in my class, I don't ask you to, well, there'll be a question on the test where you do delta H product minus reactants. If I didn't do that, I would probably run out of the chemistry community. But there'll be a question in addition to that, can you predict what's going on? And you can tell me you're predicting what's going on if we talk the same language, if we plot ln K versus 1 over T. How does it change? So which is the corresponding plot for carbon dioxide gas? So carbon dioxide subliming from solid to gas. And we've seen both these compounds now. Iodine, it's a solid at room temperature. So I'll give you that hint. You've probably not seen solid carbon dioxide at room temperature. So think about this for a minute and we'll take a vote. I'll start again. I think I was muted. So this is a tough one, and it's you should be scratching your head, and don't feel bad that you don't get this right away. You've seen it for the first time, number one. So you have to digest a lot of stuff, and then you have to bring in the conceptual part, and that's not easy. And this is coming pretty fast. And I was also saying that your student instructors pop into your room, and I pop into your rooms, but your student instructors they're undergrads this semester. They're only a year or two ahead of you, and they're seeing this in this way for the first time. So many of them. So they can see the answer and they can kind of help guide you, but they're talking with you too. That you're almost peers there as well. So let's go through this. Look at what you're thinking and go through this together. We have no idea. Equally distributed between all of them. At this one, I don't think I have. This would be a good one where if I had an explanation for each one, maybe we talk about it again. But I'll just go through it with you. So this lnk versus 1 over t thing, we know the functional form of that. So the point is, why is that not changing? The point is, we know the functional form. When you plot lnk versus 1 over t, you know the slope and the intercept. The slope is related to the opposite of the enthalpy change. The intercept is positive or negative, tells you the intercept. So slope and intercept, all you need to plot a line is the slope and the intercept, right? So can I plot this line? Oh, I had that there. That's why I do that. So can you plot this line? Well, I gave you this this hint to kind of start you thinking. Carbon dioxide you normally see as a gas at room temperature, but iodine is a solid at room temperature. We've seen it. So that tells you something about the energy that it takes, the enthalpy of these vaporizations, these sublimations. So it takes less energy to vaporize carbon dioxide, room temperature energies. It's getting it from transferring it from the particles in the room are smacking into that. That's enough energy to vaporize solid carbon dioxide. At iodine is solid. That's not enough energy in the bouncing around, transferring from the room. This has a higher enthalpy of vaporization. So I'm sitting there asking you to think about the physical process and not calculate an enthalpy from a table, although you could have looked it up. Think about what the enthalpy means. So that's energy. Getting up this hill is harder than getting up this hill. Okay? So delta H, bigger, more positive in this case for this one. So that bigger, more positive means what changes from this line? The slope or the intercept? It's the slope. Delta H determines the slope. So A is out. They both have the same slope. I tried to make them both have the same slope. They have different intercepts too. There's something different. You kind of got to have a different intercept if you change, if you don't change your slope, the only way to make it interesting is change the intercept. So A is out. B and C are possibilities. So now you see this slope change. Well, the intercept, let's talk about the intercept for a second, because that also helps you distinguish between A and B and C. The intercept is the entropy change. These two have it at the same point. But I want that to be kind of obvious to you too. When you think about the entropy change, disregard all energy changes. Entropy is not an energy. All entropy is you have something that's packed tightly together and has few microstates available to something that has lots of microstates available. So the entropy here should be very similar to the entropy here. Sure, that's carbon dioxide. Sure, this is iodine. Entropy doesn't care entropy cares a little bit the nature of the particle, but these two are similar enough particles. you have gaseous particles versus solid particles, tightly packed particles versus free particles. Tons of microstates here, fewer microstates here. Both of these entropically are about the same. Entropy closes its mind to energy changes and looks at just the number of microstates available. So solid going to gas, about the same. And we saw that. We looked at that phenomena before. So it makes sense that these intercepts are about the same. The intercept is delta S. So now which is which? Well, we said carbon dioxide, that is a greater, a lower positive number than the iodine. So the iodine has the bigger slope, bigger delta H, and bigger means steeper. Okay, so you should be able to pick the steeper one is C. Whoa, that's steep. That's not as steep. Okay? So that's the kind of thinking that I kind of want you to have. Big picture stuff. Not one number in that whole thing, but a lot of science. If you can do this, you can tell me you understand conceptually what enthalpy is. I told you this one was a gas, that one's still a solid. You understand conceptually what entropy is. Entropy doesn't care what the energetics are, completely divorced from the energetics. It cares about how many ways I can arrange these two systems. Not very many ways here and a lot of ways there. A lot in there. Here it is kind of written out if you want to take a screenshot. Oh, now take your screenshot. Sorry. Okay, let's continue. So we've said a couple times you can plot free energy changes anytime, and you can try to calculate them or measure them at any time, not just under the standard state. So we can talk about the free energy of just a reaction where it is now, wherever Q is. And I will not put the degree sign up there to indicate it's the conditions where everything's 1 atmosphere and 1 molar. So that's actually kind of more useful. This is the real world, that everything 1 molar and 1 atmosphere is artificial situation that we do because they're state functions. We can choose 0 wherever we want. So we need to have everything relative to everybody. We choose a reference. So we understand also we would expect free energy differences less than 0, that corresponds to the case where the reaction is going to go towards products. Free energy difference is less than 0. That spontaneous direction is forward. So that's the situation where Q is less than K. The denominator is too big, too many reactants. Q is less than K. And there's going to be these correlations. When the free energy difference between products and reactants is 0, universe is happy. You're at equilibrium. And when free energy difference is greater than 0, then Q is bigger than K. There are too many products. The numerator is too big. You'll go back towards reactants. So there's the same kind of relationship between Q and the free energy of the reaction as there was between K and the standard state free energy. So we should expect a similar relationship. In fact, there is one. You can decide where the free energy lies of the reaction if you can calculate the standard state, and you can get that from a table, neat, and measure Q. So you can see you can find free energy differences at any place. You can measure Q, or usually you're mixing it, so you know where Q is going to start. So you can say, how big is that bang going to be, or if it's not going to go at all. Basically, you compare the size of RTLNQ with the standard state free energy difference, and that tells you whether it's going to go or not from that state. So more useful in the real world. So I can say then that when Q gets to K, this is 0, because you know delta G is minus RTLNK plus RTLNK gives you 0. So when you get to equilibrium, the free energy of the reaction is 0. The universe is indifferent to whether I'm products or reactants. Okay, let's talk about this one together. Here, what's the free energy and K for at equilibrium now at 25 degrees C, the water going to the gas? Okay, so this hurts your brain, I know. Standard state, not standard state, Q, K. If you're at equilibrium, the free energy difference between the products and reactants is 0, as long as you're there. So if I have 0.03 of an atmosphere of water at 25 degrees C, I'm at equilibrium. The free energy difference between 3 atmospheres, or 0.03 atmospheres of gaseous water and liquid water at 25 degrees C, the free energy difference between those is 0. The free energy difference between 1 atmosphere of gas at 25 degrees C over the liquid is positive. That's too much gas. But we're at equilibrium at 25 degrees C. So K is K. 0.03. We're at equilibrium. Take that home, K. Delta G, 0 difference between the products and reactants. That's why we're there. Okay, so in this case, free energy change 0, and we know K is less than 1. K could have been any number, but we just happen to know it's less than 1. We know it in this case. That's why I can ask you this. We can also you can also intuit what K is. Your intuition is that at 25 degrees C, the reactant side is favored. You kind of know it stays as liquid water. There's not very much gaseous water. This side is favored at equilibrium. Okay, the reactant's favored at equilibrium. K's are less than 1. So you could have got that even if you didn't know the number that we've talked about several times now. Okay, so let's look at Q's. Let's mess with the reaction at equilibrium. So which is true at time T1? So here are the plots of concentrations. So you can tell what happens over time. So what's true at time T1 in this chemical reaction? Where are we on the equilibrium landscape? Talk about this for a minute with each other, and we'll take a vote. Okay, let's come back together as a big group. Push your button if you have not yet. Let me see what you're thinking. Again, we're quite spread out, about a third for every answer here. So the question is maybe reading the graph. So what K is, it's the concentrations. You measure them when they stop changing. You start the reaction, when they stop changing, that's equilibrium. You measure all the concentrations, you plug in concentrations of the products over the reactants, and you calculate a number, okay? So we have this idea that when we got to here, beyond that, they stopped changing. So here, the value of Q, which is, in this case, the reactants, B to the 2 power, because that's the stoichiometric coefficient, and the other reactant, over the concentration of C. Concentrations, moles per liter, I just measure them somehow. Okay? That stopped changing when I got to here. That's equilibrium. That is the value of K. Okay, it's nothing magical about it. It's a number you just get because you put in the concentrations and they don't change anymore. What happened when just before T1? What does that line shooting up mean? Well, the dramatic change in B1, in B, probably somebody poured some B into the beaker. So the B constant, the amount of B dramatically changed. Why did it dramatically change? Well, we don't know, but it did. So not at equilibrium anymore. This is the equilibrium concentration of B. And now we have a situation that's not at equilibrium. And how did it change? Did Q get bigger or smaller? Well, we made that bigger. So it was K. Did I? Oh, I'm glad you guys are watching. Yes, stop me when I do it. Sorry, guys. Thank you for watching. It's products over reactants. C over B squared. Hey, Joe Chemist. It's always the case. I'm bad at details. That's an important detail. That one I should not be bad at. I learned very early on in my scientific career. I was bad at details. I would always get the numerical answer messed up because I'd give a sign error or I'd do something wrong. Conceptual part I got, didn't get. I would be bad with details. So let's get it right. Products over reactants. We talked about it, right? And I just talked about it with this group. So C is on top. Everything else is the same. Okay, we still just changed B. So I'll draw my arrow again. We just added some of that. So how Q changes depends on what that is. You added a reactant. That's in. You made the numerator. I said it all wrong again. You made the denominator bigger. So if you made the denominator bigger, what did that do to Q? It got smaller. K is still K. K isn't going to change. But this, that thing, it's not an equilibrium value anymore. That got bigger. So denominator getting bigger, Q got smaller. So Q is going to be less than K. Okay, you added a reactant, Q decreases. The reaction will go, you added a reactant, the reaction will go and make more C. So we could continue to plot it. Hard to tell exactly what will happen, but B will change and C's a product. So we'll get some more C, and we'll use up a little A. Okay? Those are different, but if I took now and weighted and measured all those concentrations and plugged them back in, they would also equal K. There's a million different combinations that can equal K. That's still equilibrium. The value of K is still K, even though the concentrations are different. There's a lot of different concentrations that will solve K. So there's some dynamics for us. Okay, let's do some numbers. We'll throw in some nuts and bolts here. Free energy difference for the following reaction given the under the given conditions at 400 Kelvin. Will the reaction move towards products or reactants, or is it at equilibrium already? So I have some pressures. These are in bar. It doesn't matter what unit you have. And a lot of people ask that question. You have the concentration squared or the pressure squared. What are the units of K? As far as we're concerned, K is dimensionless. It's dimensionless. Put in the numbers essentially that I give you. If I give you a pressure in bar, put it in a bar. If I give you an atmosphere, put it in atmospheres. I give you a moles per liter, put it in moles per liter. Do the ratio products over reactants, please, and calculate a number. Okay, that number is what you need. So we can calculate a number, if I can write the equilibrium expression correctly, of the product pressures over the reactant pressures, because I know them. So let's do that. Here's the reaction. I can write an expression for the dynamics of the reaction, this mass action expression. It's not K yet. It's, well, we don't know. We're going to check if it's K. So we have those values. Let's put in the pressures, 21 bar for the ammonia and hydrogen and nitrogen, those respective pressures, and calculate a number. It's 18. So K at 400 K, somebody told me it's 41. So am I at equilibrium? No. I have to get to 41 somehow. These have to rearrange till they get to 41, some combination. We know kind of what's going to happen to the various amounts. Maybe not exactly, but we know K here is quite a bit larger than where we're at. So if K is large, K is larger at equilibrium, I have to get the numerator bigger and the denominator smaller to make that number bigger. So the numerator bigger, that's products. Numerator smaller, that's reactants. Go and make more products. So we're not at equilibrium. We'll get there. Q is less than K. Reaction proceeds towards the products. I could calculate now, since I have a Q, I can calculate the free energy difference at that point between the products and reactants, not standard state, not where everybody's 1 bar, 1 bar, 1 bar. That's how I would get that number, delta G standard. To get this number, what the free energy difference is right now, I can take Q, put it in there, get the standard state free energy. Okay? Now, here's the kind of question I might ask you, because if we go back one step, here, and I ask you, what is the free energy difference instantaneously right now? Well, you know, on your equation sheet, I will give you an equation sheet. And in fact, it's already posted, and I'll make sure it's posted. I'll put it somewhere more obvious. It's the equation sheet you use for every exam. So you could look at it and get familiar with it. So you'll have this expression. You don't have to memorize any physical constants. You don't have to memorize those values. You don't have to memorize any equation. You'll have them as a reference on the when you're doing the exam, and all in one place, so you don't have to search too hard. if I asked you to do this question and said, well, what is the value of K or delta G here? You'd say, oh, well, I know this. So you would go to calculate this. And a lot of you would complain, I don't have enough information to get the standard state free energy difference. Why? Because you didn't give me a table. You didn't give me the standard free energies of the products so I could do products minus reactants. Okay? I kind of was hoping you knew one more thing. If I give you K, I do give you that number. K and the standard state free energy are locked together. So you have, and it's easy, much easier to plug 41 in there than it is to calculate, look up all the products and reactants and do delta G products minus delta G reactants. So we can do that. Delta G minus RTLN K, there's R, there's K, T, and K was 41. So make sure you use an R in the correct dimensions. This one's joules per Kelvin mole. You're canceling Kelvin there, so make sure you're in Kelvin. You'll get joules per mole, and it's minus 12 kilojoules per mole. Does that make sense to us? Well, we said the reaction is going to go towards products. Yeah, products are downhill. Delta G right now. Oh, I'm sorry. This is the standard state. The standard state says products are favored. But even where we mixed it up, the products were favored. This number says if every pressure was 1 bar, that pressure was 1 bar, that pressure was 1 bar, that pressure was 1 bar, then it would still go towards products. Products are downhill. And even where we mixed it up, isn't it? Go towards products? Well, yeah, because we looked at Q. So we can compare that. Now I can calculate what this is. I have this number, the standard state difference. I calculated a Q before, it was 18. So I can plug those numbers in. There's the standard state free energy difference if every one were 1 atmosphere or 1 molar. Here's the value of Q. That tells me at the position I'm at, the products are even more favored than they are in the standard state. Okay? Wonderful. These I gave you in the notes, so you don't have to take screenshots of any of that. And you always go, you can replay it. Oops, looks like it's going to play again. Oh. I'm not sure what that is. This is another case where I edited it. We got into a case, I remember last week, or maybe the beginning of this week, we had a ChemQuiz, and I couldn't figure out what was going on. It was the entropy of the universe or something. The reason that happened is I had edited it. I changed the quiz, but not changed the solution. So the solution wasn't right. And I'm sitting there, what the? So this is one of those cases where I think I changed the problem, and this is the old solution or something. Got to be more careful with my editing. Okay. So why don't we say that is all you need to know for the midterm? Okay, we'll end at on the syllabus. I think that there's a title for the topic, and it's free energy and equilibrium. Stop there. The next thing is kinetics and thermodynamics, and we'll pick up there. I'm going to talk about it a little bit. Don't zone out too much. I could either review kind of for the midterm now, or we could do it Tuesday because the midterm's in the evening. Oh, wait, well, we can ask. We can do some midterm review right now, or do the midterm review Tuesday after you've had some time to study. Would you like to see me do some review now, or just wait and see review? We have the good thing is we have the class at 8, and you don't have to take the exam till 6. So the review can help you maybe more after you've studied. But I will ask you, would you like A, review now, or B, review Tuesday? Okay. Bang in quickly. Tell me what your preferences are. Okay, let's get a little more than half of you. So hopefully it's reflective of what you're there. So the difference between this number and some other numbers is these are the people that I think are actually awake. Some people are sleeping in front of their Zoom. Okay, let's stop that there. Ding. Stop that. Poll, that's most of you. Most of you would rather just see the review on Tuesday. I think I agree. The review will be more useful if you've studied. And you got several review sessions, as you saw, coming up. So we'll do that. But the good thing is the first part of this kinetics is a review of the thermodynamics, which is going to help you anyway. So we're going to talk about more of these pictures now. And you can see already from this preview of the lecture, we're going to get into some detail that we kind of already know, but there are parts that we don't know yet. So we're trying to understand this picture, water gas being formed. This, if I said I have 1 atmosphere, or if I do this reaction here, hydrogen and oxygen going to water gas, that is the chemical reaction that we call the enthalpy of formation of water. And that's something you should kind of know. Why does this one have kind of a name? Well, enthalpy of formation of water is the formation of the compound from the elements in their standard state. So if that's hydrogen gas, that's oxygen gas, and that's liquid water or gaseous water, whichever one you want to know the heat of formation for. So if that's liquid water, this represents the enthalpy of formation. It's a special one, give it a name, of water. So it's not just any old reaction, it's one you could find in a table because we plot those, we record those. So this one you could look up. And if you tried to do it, enthalpy of formation, you'd look up enthalpy of formation of water minus enthalpy of formation of oxygen and hydrogen, and you wouldn't find those two in the table. Why is that? Because they're the elements in their state, there's 0 enthalpy of formation. So there's some review already. Now, if I just calculate that from the table, though, I look this up, then that's the situation where everything was 1 atmosphere and 1 molar, the formation of water under those conditions. Maybe not how you would have done it, but it's the number we use as the reference. So we have reactants and products. We've seen this now many times. That explodes. It explodes, as far as we're concerned, spontaneously. Even though that balloon will sit there forever and not explode with hydrogen and oxygen in it. In terms of our parlance, thermodynamic parlance, that reaction is spontaneous because at equilibrium, the products are favored. It's downhill. Okay? So spontaneous, when you got to this class, maybe you thought spontaneity was the actual explosion, but that's not what it is thermodynamically. It just means this is where you end up. Free energy of the products is lower than the free energy of the reactants. So if I'm plotting free energy, I can plot the reactant free energy and the product free energy. Now, a minute ago, I was talking about enthalpy. So this could also be an enthalpy axis. But in this case, I'm choosing the free energy difference between the products and reactants. And in this case, they're the same sign. Enthalpy, that explodes. Enthalpy is downhill. And in this case, free energy is downhill. We know 2 things. Sometimes enthalpies are positive, but free energies can still be negative. It can still favor uphill enthalpies, those reactions go spontaneously. We saw some reactions that absorb energy. So free energy is kind of better to plot because it tells you really what happens. Gives you an idea of what K is. Where is it at equilibrium? You can't tell where it is at equilibrium, where it ends up, just from the enthalpy. If I did enthalpy and it was uphill, and delta G also happens to be downhill, that means there must be a big entropic component that makes the free energy negative. Enthalpy isn't helping you get down free energy hill. There must be an entropy part that makes you get down free energy hill. Okay, so this exothermic, this release of energy, is the thermodynamics. Everything we talk about here is these areas are all thermodynamics. And when we talk about thermodynamics, we're always talking about the equilibrium situation. So that means this value here at equilibrium, that's a free energy difference between the product and reactants. That free energy standard state would give you the K, and you could tell that this is negative, K is bigger than 1. Favors the products. So this part we've talked about a ton, the lower portion of the curve. This we've talked about a little bit. We said, well, to get there, there's a hill in the middle. There's a energetic barrier. That's what keeps the hydrogen and oxygen on this side and not making water readily. You have to add the flame. You have to give them this much potential energy or kinetic energy. You have to give them this much more total energy from the flame, added as kinetic energy, converted into potential energy. We're going to start breaking and forming bonds. So give it energy, and then it'll roll down to the eventual products. This part is kinetics. This is the active part. This is time dependent. This part is not time dependent. Products, reactants, I'm talking about the equilibrium state. I'm talking about the boring state at the end of the road. So we're going to briefly talk about kinetics. We're not going to do a lot of kinetics. Basically, what I want you to know about kinetics is this part, that there's an activation barrier, an activation energy to get from reactants to products. You'll hear this all the time in your biological classes. Well, I can't get there. There's an activation barrier. I need an enzyme to break down the activation barrier. And scientists will, you guys probably don't do this in your normal lives. Maybe you will after this. You're sitting on the couch. You'd be happy you're riding your bike, but you don't want to get off the couch. There's an activation barrier. Your happiness plots like this. Be happy you're riding my bike. However, I have to get off the couch. There's an activation barrier between you and your bike. Yeah, use that with your friends and family. They'll see what reaction you get. There's an activation barrier. I'd be happier if my room were cleaner, but so this energy, we call it the activation energy. That's how much energy I require from the surroundings to get to that point where I can get to those products. Okay? That is a kinetic thing. I get that from bouncing into the environment. The energy being transferred from somewhere. I don't have enough on my own. I get that from somewhere, the surroundings, and I get downhill to products. We talked about that. So we're going to enter a new domain here, and we're going to kind of look at what we were just talking about. Kinetics tells you what's happening in this part of the curve. So here, the concentrations change. You start out with initial concentration of X, or in this case, it looks like it's a product. You start out with little x and you make it over time. Once you get here and it stops changing, that's equilibrium. That's thermodynamics. So from here to here, it's kinetics. This is where I'm getting over the activation barrier. Here, I got there, and I'm in equilibrium with reactants and products. So that part is kinetics, and that part is thermodynamics. Okay, so this line has a slope, and in this case, it's relatively constant slope for most of the time, and then the reaction starts to slow down towards equilibrium. The reaction rate is the slope of that line. Going really fast, and then going as fast, and then stopping. And in this case, it's not stopping, it gets some constant rate, and the reverse reaction has that same constant rate. That's what equilibrium would be. So factors that affect the rate, and I think you have this might make sense to you. Factors that affect the rate, how fast I get there. Well, if you have relatively more of your reactants, you have higher concentrations, and I've got that 0 there, initial concentrations times 0. So if you have more to start with, there's more possible collisions to have. So if you have A plus B going to C, you got more A and B, higher concentration, and we should say that, not just more densely packed together, higher concentration, more collisions, faster reaction. So we're back to this microscopic interpretation of particles bouncing into each other. The more collisions I have, the more likely I'll get a reaction between the two. Not all collisions are successful. It's the ones that have that activation energy when they come together. Those are the ones that go. Other collisions aren't helping you. Okay? A catalyst could help you. We talked about what a catalyst does. A catalyst increases the rate of the reaction by lowering the activation barrier. If you put a catalyst in, now more of your collisions are successful because it lowers the activation barrier. You have a broad distribution of energies in your sample. Some are moving fast, some are moving slow. You got a bunch of collisions. Some have enough energy to get over this barrier. Bam, that was a high energy. Those two reacted. Others, not enough. They stay reactants. If you lower the activation barrier in the same sample, now more of those collisions, even the lower energy ones, go to products. And you get the reaction going. So catalyst increases the rate, but here's a very important thing, and one of the most important take-home lessons. You still get here. Ooh. Don't touch it. You still get here. You still get the equilibrium. The thermodynamic part doesn't change just by adding a catalyst. The kinetic part, you get there faster, you lower the activation barrier. You got to get from the couch to your bike. What could lower that activation barrier? Well, a friend comes along and says, come on, let's go biking. Catalyzes you. You're the catalyst I need to get on my bike. What a friend. Your best friends are catalysts. Okay, we have a few minutes. Let's look at a ChemQuiz. We'll talk through it. And we'll finish up for today. And I have office hours after today, so you can't ask questions. I think we'll stay on the live stream. We'll capture it. So everybody can benefit from the questions. Okay, so shown in yellow are the reaction profile for the 1-bromo product here. So I have two chemical reactions. They're a bromination. I'm taking this hydrocarbon, I'm adding this hydrogen bromide, and the bromine can either stick on this guy or it can stick in that position. So it can brominate in this position or brominate in this position. This is the bromine on the end of the chain, and this is the bromine in the middle of the chain. So they're different molecules. But you're going to learn this and study it in your next semester of chemistry, organic chemistry, that the rates of these reactions don't have to be the same. And we can see, if you wait an hour, you run the reaction for an hour, you get the reactant yellow here, the 1-bromo. If you wait a longer time, you start to get more of the 2-bromo. So what does that tell you? This is the 1-bromo, in yellow. The dotted green is for the 3-bromo. And there you go, organic chemistry. It's not 2-bromo, it's 3-bromo, because organic chemistry says you have to start counting from where the double bond is. 1, 2, 3 bromo. So which is which? Well, what is this kind of telling you? Time isn't a thermodynamic variable, but what it looks like here is if I were to wait a very long time, it looks like what's happening is the 3-bromo is building up over time. So all of them are in equilibrium, but it looks like that guy happened fast, but this guy looks like he's going to win the race. Can't tell, but he's building up and he's dropping over time. So what does that say? Well, initially, you got lots of the yellow. You got lots of the 1-bromo. So it was easier to make the bromo. So I would say that the bromo activation energy, the 1-bromo activation energy, is lower, just easier to get here. So initially, you make a ton of it. That's a kinetic effect. But now thermodynamics starts coming into play. So I think it's either B or C. Oops, wait. A or B, because that's where you have the lower activation barrier for the top reaction. Here, you'd expect to get make the 3-bromo, the green one, faster. But then over time, so I gotta choose between A and B. Then over time, what's the thermodynamic difference between the two? Is the B compound the more thermodynamically favored? Will there be more of that at equilibrium? What is favored at equilibrium? Well, thermodynamics tells you that. I'm headed towards equilibrium. That difference tells you who's favored at equilibrium. So it looks like what's happening is the green one, the 3-bromo, is favored at equilibrium. So I'm going to sketch that lower thermodynamically. Higher kinetically, doesn't happen as fast. But if I wait long enough, it's the energetically favored one. So you can see it happening. Oh, you make a lot of this one. But it's still bouncing around. Every time you make one of these, it tends to stay there more than these, because it's at a lower portion. So going backwards for the yellow one is easier. And once you do it, you have another chance of making, once you go backwards, you have a better chance, you have another chance to make a green one. And if you do, the green ones are harder to convert back. So it builds up here at that low energy thermodynamic, favoring the green overall. Okay? That's beautiful. If you understand that whole, that's almost all I want you to know about the difference between kinetics and thermodynamics. Maybe we'll do a little bit where we actually calculate a rate, where we'll plug in the concentration and see what the rates are. But that's the big idea. Okay, so we'll stop here, and office hours start now. for me. So we'll keep the live stream running. Ask your questions in the either in the Zoom room. Can you just close all the? We'll bring you all together in the Zoom. That way, actually, there'll be a little glare, but I'm gonna join the Zoom. You can ask me, ask the prof, face to face. That unfortunately though, that monitor gets a little glare right here. We'll mess with it. I just want to see. So if you have a question, turn on your mic. Go ahead and ask me in the main Zoom. Okay, do we have questions coming in? Hi, everyone in the class. Any questions for me, office hours? And again, science questions are the best ones to ask in office hours. Anything coming in? Chat, on the chats. Yes, go ahead. Hi, is this Amanda? Sorry, Amanda, you probably hear me twice, once in your Zoom and the little delay on your live stream. Go ahead. I can hear you, Amanda. Go ahead, ask your question. Great. Yeah, great question. So, Amanda, where are you sitting in the world right now? Okay, I'm just going to do it radio call-in style. Amanda from San Francisco asks, in that ammonia reaction where we were making ammonia, so I'm going to do this. And Sydney, could you reach behind and just push that screen that way a little bit so it's not glaring off this one? Thanks. So Amanda asks, we saw this chemical reaction, and it was N2 gas plus hydrogen gas, the elements in their standard states, and that makes ammonia gas. Let's balance that. So we need 3 over there. If we do a 2 there, that'll give me 6. I can go 3 there, and we already got 2 there. Cool. Okay, so Amanda asks the question that actually should be in your mind. I said to make this reaction go, it's exothermic. Okay, delta H is negative. And I said the best combination, or a very good combination, was high temperature, T, I forget what it was, but it's pretty high, like 500 Kelvin or something, and quite high pressure. P of everybody, I think, was something like 200 atmospheres. This is a ridiculous high pressure. Crushing, it would just crush virtually everything. High temperature. Amanda says, well, wait a minute. You also told me that high temperature, since this is exothermic, I might put heat as a product, and that would have the equilibrium move that way. High pressure has, well, if you have high pressure, that's lots of particles. Lots of particles mean I would go towards the fewer particle side. I would go this way. So the temperature effect is making me go that way. The pressure effect is making me go that way. How do I know which to pick? Well, in a first, let me say on the exam, I'm not going to. I won't give you a situation like this where there's two factors affecting the equilibrium. I'll tell you that the experimental conditions, they just tried this in a bunch of different ways, and that they found that that condition gave them the most ammonia. So they found it. But what they were doing was battling the kinetics and the thermodynamics. So the kinetics were saying, let's get a lot of collisions, very high energy collisions. That helps me get over my activation barrier. So it increases the rate of the reaction. And let's also favor it by putting a lot of particles in. High temperature, lots of particles. So they got the reaction to go fast, and increasing the pressure favored this side, and it also just helped you have more collisions. And you know what they could do is they could do what those bromine people could have done. If you wanted in that last example, the 1-bromo product, then do the reaction and stop. Do it for an hour and stop. That's when you get the most bromo. And when the 1-bromo. So that's in the real world what you would do if the equilibrium doesn't favor this, if thermodynamics doesn't favor this, you can still make it go fast and then pull the product out as fast as you can before it thermodynamically goes somewhere else. Thermodynamics takes time, kinetics doesn't. So the answer is, number one, I'm not going to give you anything on the exam where you have two things battling each other. Number two, it's as long as you know the pressure effect favors that side, the temperature effect favored that side, and in this case, the pressure effect wins. But I told you that. That's how we did get a lot. That's all. You didn't have to know which one wins. I told you which one won. It was the experimental result. Great. Other questions? Or does that help, Amanda? Was that it? Oops. I'm not there anymore. Oh, you stopped my video. Okay. Okay. Someone else. Any other questions out there? And you can ask, if you're shy, you can ask it in the chat. It's okay. I just like to talk to people. It's post-COVID. I want interaction again. What do you got? I love that question. Lucille, where are you sitting? Fremont. All the local girls are asking questions this morning. Lucille in Fremont says there's these ginormous magnitude differences between enthalpy differences and entropy differences in chemical reaction. So she noticed that entropy differences, it's usually a few joules per mole Kelvin, and enthalpy difference, it's kilojoules, and usually hundreds of kilojoules in per mole. So we saw those two things battle each other to determine whether you're going to be spontaneous or not. Sometimes they work together. Enthalpy goes downhill and entropy goes uphill, and that is good. That just makes you more favorable at all temperatures. But sometimes the enthalpy goes uphill, and then you need the entropy to go downhill, or you're never going to be spontaneous. So you have to go, and this I think is Lucille's question, you have to go to high temperature to get that one to go, because that it's minus T delta S. So the T makes a big difference in the entropic part, but it doesn't make any difference in the enthalpic part. The entropic part is all about how many combinations you can get, and more higher temperature, more combinations, more motion. So the entropic part depends on that. The enthalpic part doesn't really matter if you do a reaction at 100 degrees or 0 degrees. The enthalpy difference is about the same, the amount of energy released, because it's in the bonds usually. So the question is there some kind of theoretical limit? The theoretical limits are only the limits achievable. That is, how high a temperature can I achieve? How low a temperature can I achieve? But in general, in principle, no. In general, yes. There are limits. The interesting thing I think about the universe, one of the interesting things about the universe is, and since we're chemists, temperatures around ambient temperatures are kind of the temperatures where it's interesting, where those things are really in a relatively delicate balance. So you just go a couple hundred degrees away from room temperature and you find entropy making a big contribution. You go a couple hundred degrees down in temperature, entropy makes a good bigger contribution, but it's enough of a contribution that you see free energies changing. So that's kind of the big picture. Does that help at all, Lucille? It was kind of a great. Anyone else want to chime in? Looks like there might be something coming in the chat. I can't read it. Can you see the? Are you in the Zoom, Leo?
For the equation for the reaction quotient, is it going to be the issue is the pressure has to be taken for reactants and the concentration has to be taken for the products, or vice versa?
Oh, great question. That's one of those details, and you already know I'm not a good detail guy. The question is, we talked about K and the units of K, or the units of Q. So you're putting in products and reactants. Some of them are gases. Some of them are in a condensed phase. Some of them are in soluble phase. What do you put in? First of all, in our case, it doesn't matter. I'm going to give you some concentration or pressure in some units. You plug that one in, and you plug them all in. You plug in, if I give you an atmosphere, and if there are gases and things in solution, plug in atmospheres and concentrations, and don't worry about the units. So K and Q are going to be dimensionless as far as I'm concerned. We're going to ignore the units. And indeed, we put concentrations and pressures when we're talking about it in general chemistry, but the equilibrium expression there, it's actually not the concentrations and the pressures. It is their spontaneous free energy. It's their free energy under exactly those conditions. So, and that just happens to be related to the amount that's there. So a real equilibrium constant is dimensionless, because what you're really talking about is the activities, the relative free energies that they have in that state of that compound in that. That just happens to be linearly related to the amount that's there. That's the biggest contribution. So you really have a ratio of free energies. We just express it in terms of something that's proportional to, and that is concentrations and pressures. And yes, put in any old one you want, that I give you. Does that help? Okay, other things? Yeah, great question. So the question, this is, Swati, we've spoken before. You added the class a little late, I think. Yeah, we spoke to you in a Zoom. And you're here. You're in San Francisco or something? Oh. Oh, yeah, I got that wrong. Okay, so Swati from Texas says, thank you for that question. Swati from Texas, a longtime listener, first time caller. Love the show. Now I forgot the question. Oh, the question is, we write these reactions, and it's a very insightful question. I like the question. You have A going to B, and we're thinking about what I told you is when you get to equilibrium, then the entropy is 0, and maybe I misspoke. Entropy is not 0. The entropy difference between these guys is 0. The entropy, when you get to equilibrium, when the change going from A to B disrupts the universe the same way as the other way. So you have a little bit of change of entropy when you go there. You have a little bit of change of entropy going there. And they just happen to be equal and opposite sign. So maybe I create more microstates here, I create fewer microstates there, but it's the balance of those two entropy changes at equilibrium that get you to that equilibrium space. And what we say is it's not the entropy, it's the entropy of the universe that's 0 at that state, not the entropy of the individual particles. So you have to take into account the universe, which is a pain. So B going to A disrupts the universe by some amount. A going to B undisrupts the universe by an equal and opposite amount. And the universe says, okay, do either one of those. The idea is when I go from A to B, that entropy change just, even though there's a total entropy, the little changes are balancing each other. Okay? Right. Great. And it's the special difference. It's the difference between the products and reactants. So the instantaneous entropy difference between these guys in this conditions and these guys in this conditions, that there's a number for both of those. Entropy change of the universe, they balance out, is 0. There's a universe entropy change that's 0. Hard to track that. That's why we have free energy. But the individual reactions do have an entropy change associated with them. Okay? Other things? I love the question, thinking deeply about what's going on. What else? Okay, so the question is from Heidi K. Heidi K. How do you say your name? Okay, Hide says there was a question in a quiz or a homework that compared bond energies with enthalpies of the reaction. And let me say first, for now, you don't have to be able to do that. That question sounds like it snuck through our filter. We haven't talked about bond energies in particular yet. The short answer is if you could, the enthalpy of the reaction is coming from the bonds breaking and being formed. The difference between the bonds that are broken and the bonds that are formed, and maybe a little kinetic component, is the enthalpy difference. So in principle, absolutely. If you know all the bond energies exactly, you could take bond energies of the products minus the bond energies of the reactants and get that number should match very closely the enthalpy change you get from the standard state table. So global answer, yes, you can do it. Specific answer for Tuesday, you don't have to do it. Okay? Other things? Hi, Lucille. Yes. So the question is, in equilibrium expressions, whether they be Q or K, that is whether they be kind of an instantaneous one or a number that's at equilibrium that you either calculate or you get from a table. Pure liquids and solids do not occur. How do I know which ones are pure liquids and solids? In particular, water, because it's there all the time. So first part of your answer, yes, water is a pure liquid. And if water is produced in the chemical reaction and the chemical reaction, certainly if the chemical reaction is occurring in water, but pure liquids and solids do not appear. It's just a conventional thing. So how do you tell whether they're pure liquids and solids? I'll tell you. I will say pure liquid water reacts with this and that to form this and that. Solid, any solid is the pure solid. If you see the S in there, then that's the pure solid. If you see, in fact, yeah, that's a good way to do it. I'll try to be very careful. I'll write the reactions A plus B going to C plus D, and if you put in parentheses L or in parentheses S, those are pure liquids and solids. Everything else, it's a mixture. It's a compound it has some concentration or pressure. So if it's a gas and it doesn't have pure liquid and pure solid, then that's how you'll do it. That way we'll all be on the same page. Okay? All right. Looks like everyone's leaving the Zoom. Any questions from the, looks like maybe 3 of you that are still here? Yeah, are there really just 5 of us in the Zoom? Okay. Oh, there's a text. It's just a thank you. Well, you're welcome, George. Hope things are going well. Bye, everybody. We'll see you Tuesday, and we'll do a review. No problem. Go ahead. And please call me Mark. You don't have to do. We're all friends here. No. Sorry, I'm glad you asked that because Q does equal K, and not 1. Well, I mean, unless K is 1. So at equilibrium, Q equals K is all you have to take home. This can have a lot of numerical values, but these are the constant ones. But it can have a lot of numerical values, a lot of different reactions. It might coincidentally be 1. It's doubtful because for that to be 1, all the pressures and all the concentrations have to be 1. And that's pretty rare. This K equal 1 is would be equilibrium. The standard state would be equilibrium. That is not likely to happen. Q could be easily 1 because you could just pour 1 molar of everything and have 1 atmosphere there and start there. But when Q gets to K, then you're at equilibrium. All right. Good luck. Take care.